Everybody. My name is Martin. I'm a co-founder at Zircuit, and I will be telling you a little bit about how we do sequencing and what we do differently in our sequencing protocol. So, first of all, Zircuit is a novel zero-knowledge rollup. We are fully EVM compatible, and we use AI to prevent hacks. So that I can tell you how, we have to first take a look at how sequencing normally works. So, in any kind of rollup, we have some service called the sequencer, and the role of the sequencer is to collect transactions and organize them into blocks. So sequencer is over there, it's collecting those transactions, and whenever it has enough, it produces a block and appends it to the L2 chain. And because this is a rollup, we also have an L1 that we are trying to scale, right? And every once in a while, we take the state of the L2 chain, we take the state root, which is a representation of that state, and record it onto L1 inside of some smart contract. That's how rollups work. So on Zircuit, we do a little bit more. The setup is exactly the same. We have the L2 chain, that's Zircuit, right? We have sequencer that collects the transactions. But the sequencer, with every single transaction, instead of right away putting it into a block, it asks, hey, is this transaction safe? Or is it here to cause harm? So it has some kind of an oracle. This is the AI that we are using. That oracle accepts the transaction and the trace and the effects of this transaction on chain and asks this question, is this safe? And if it is safe, meaning that it doesn't cause any harm to any users, to any protocols, then everything happens as it normally would. The transaction gets organized into the next available block. If the answer is no, the transaction is not safe, then instead of placing this transaction into a block, we place it into the quarantine. And the rest of the principle remains the same. So we have the chain, it is ticking, and every once in a while we take that state root representing the state of L2 and we record it into a smart contract on an L1, okay? So I want to show you how this works on a sort of practical example because I also have an implementation demo later. So the practical example that I want to portray is this type of a hack. We have some smart contract, we will be calling it the victim pool. And the purpose of this smart contract is to hold some ERC20 tokens and sell these tokens to general users of the blockchain for exactly the same price as they are currently available for on Uniswap, okay? So for the sake of an example, let's assume that we have a pool and that this pool holds 30 million of these ERC20 tokens and it has them for sale. Then I said that we will also need Uniswap, right? So this will be the classical version of Uniswap v2 that we are familiar with. And the liquidity for this example that we will be assuming will have 30 million of tokens paired with 30 ETH, right? So at this kind of pairing, Uniswap would be selling 1 million of tokens for 1 ETH. And then we will have an attacker, and the purpose of the attacker, or the intention of the attacker, will be to steal as many tokens from the victim pool for as unfair price as is humanly possible, right? So they will want to play the victim. And so that we can somehow manipulate the market and actually mount such an attack, we will also need a flash loan provider. So the flash loan provider is another smart contract. It has liquidity, it has these ERC20 tokens, and it is capable of lending these tokens to other smart contracts for the scope of a single transaction. So if at the end of this transaction the borrower repays the flash loan, the transaction will remain on chain and will be successful. Otherwise, the flash loan provider is going to revert it. So with this setup, this is obviously a vulnerable system. The victim pool is vulnerable. So the attack would work as follows. At the beginning, the attacker contract is going to borrow all those tokens from the flash loan provider. Okay, so the flash loan provider will know that the attacking contract owes them 30 million tokens, and the attacking contract will have the 30 million tokens available to their disposal. With that, they can go to Uniswap and they can actually dump all those tokens, sell them, right? So Uniswap will buy 30 million tokens and the attacker will end up with 0 tokens, but instead they will get some ETH for them, right? So the balance in Uniswap changes. It no longer has 30 million tokens paired with 30 ETH, but it has now 60 million of those ERC20 tokens paired with roughly half of that ETH that it originally had, so 15 ETH. And the result is that Uniswap now enters manipulated market state because it sells 1 million tokens for much less than 1 ETH, right? In exchange, the attacking contract obtains some ETH. So it can now go to the victim and say, hey, I have some ETH and I'm going to buy some of these tokens from you, right? For the price that they are currently available for on Uniswap, but that price is being manipulated. And because we want to maximize the profit, the attacking contract is not going to purchase all the tokens that the victim has, is going to purchase only roughly 10% of those, right? So let's say 3 million. So we go and we buy 3 million tokens from the victim. The victim is going to ask Uniswap, hey, what is the price of these tokens currently? Uniswap will say the price is actually very low. You should only accept roughly 0.75 ETH for them. So this is what the victim is going to ask for. The result will be that the attacker is going to obtain 3 million tokens that it bought from the victim. It will still have some ETH left, right? And the victim will have much less tokens by 3 million and very little ETH. Now you can see the unfairness there, right? Because we wanted to sell 1 million tokens for 1 ETH, but the victim actually only received 0.75 ETH from the attacker. And then, because the attacker received some tokens, he can use them for extending this manipulated state. So it can actually go to Uniswap and say, hey, I'm going to sell you 3 more million tokens, give me some ETH back, right? And we will be doing that in the loop. So after doing that, Uniswap will be even more manipulated. It will now have 63 million tokens paired with less ETH. And the result will be that it will be selling tokens for much, much less than what we wanted to initially. Attacker will increase the amount of ETH that they obtained. It will have 0 tokens, but that means that they can again go to the victim and purchase more tokens for a cheaper price, right? And then we rinse and repeat. And in every single iteration, the balance of the victim pool will be slowly being depleted. The attacker will be obtaining more tokens. It will be selling them again on Uniswap. And with every single sale, the manipulation will be increasing its effect, and Uniswap will be selling those tokens for less and much, much less and much, much less and much, much less. Okay? Then at the very end of this process, the victim will have almost no tokens left, right? But because we were purchasing them for an unfair price, it will also have received almost no Ether for them. It will have received much less than it wanted to. The attacker will, on the other hand, end up with a lot of ETH. And in the end, Uniswap, because this is where we were selling all these tokens, will be selling the tokens for extremely cheap, right? It will have all the tokens in the universe, and it will have almost no ETH paired with them, because it was, releasing that ETH to the attacker. So at the end, we can actually go back to Uniswap and say, hey, I have all this ETH. Please sell me all the tokens that you can for this ETH. So we will restore the balance in Uniswap, because that's where we originally started. So it will have roughly 30 million tokens, roughly paired with 30 ETH, ignoring all the possible fees that are happening here. And the attacking contract will then have the original 30 million tokens that it borrowed, right? Because it purchased all of them back from the Uniswap, plus all the tokens that it actually stole in the process. So it can come back to the flash loan provider. It can close the loan of these 30 million tokens. Flash loan provider will be happy, and it will end up with all the tokens that it stole. So the result is that the victim pool will be nearly drained. There will be a lot of damage, and the attacking contract will actually have a large balance. This is how the hack works. So what I did for the purposes of this talk was that I actually implemented it. I implemented all the smart contracts, and I ran them through hard hat simulation so that I can see that this attack actually works, and I'm going to show you how that implementation works. And then I took all those contracts, I deployed them on Zircuit, because Zircuit has that AI-enabled sequencer level security, and I will show you from a video how that experience looks for the hacker on Zircuit as opposed to normal Ethereum network. So let's quickly take a look at the implementation. So this is the implementation of the smart contract of the victim. It's a regular Solidity-based smart contract that maintains a reference to the token that it's going to be selling, to WETH, because that's our representation of ETH on Uniswap v2, and it will have a reference to the Uniswap router. Nothing specific or nothing special happens inside of the constructor. It just initializes all these references. But most importantly, the logic of the victim is implemented in here in the function called buy tokens. So function buy tokens is payable. It receives some amount of Ether. Then I will show you on the next slide how this quote tokens for Ether is implemented, but we essentially ask Uniswap, hey, what is this Ether worth in the tokens? Then I have some logging statement for the sake of simulation so that I can visualize the progress of the hack for us. But in the end, that smart contract is going to take a look whether it has enough tokens in it, and if it does, then it transfers the respective amount of these ERC20 tokens to the buyer. The function for quoting the number of tokens is purely referencing Uniswap. This is how we wanted it, right? So we have a direct liquidity pool. We specify that the sell path is from WETH going to the token, and then we just say, hey, Uniswap, how many tokens would you give me? This is this get amounts out for this particular amount of Ether, and we return that. That's how the quoting for the market works. So then we have the flash loan provider. The flash loan provider uses the typical implementation. It has a function called flash loan where I can tell the flash loan provider how many tokens I actually want and provide some additional call data parameters that will be passed back during a callback to the borrower. So the flash loan will take a look how many tokens it is loaded with. Then it is going to send over the requested amount to the caller of this function. Then it's going to call back to the caller of this function and call function execute operation and transfer the execution there so that the attack can actually happen. It assumes that somehow it will be repaid, all those tokens that it lended to the attacker. And then at the end, it checks that the amount of tokens that it ended up with is actually at least what it started with, right? Otherwise, it's going to revert on this line, and then we have some logging event that is being emitted. So this is the flash loan provider. Then we have the exploiter. So the exploiter keeps a reference to the flash loan provider so that it can ask for the loan. It keeps reference to Uniswap so that it can be dumping those tokens on Uniswap and can be manipulating and manipulating. It has a constructor that does nothing special other than initializing those addresses. And then it has the entry point for the attack. So here we initiate the flash loan. We ask for some amount of ERC20 tokens to be borrowed. That will be 30 million. We also know who the victim is, and we will be passing that as a parameter that will be passed back to us. Then we call the flash loan provider, hey, give us a loan, right? This is where we receive those 30 millions of tokens. And then when the flash loan provider calls back, we execute the operation. So inside of execution of the operation, we decode who the victim is. We define a sell path for selling the tokens on Uniswap. And then we are going to launch a loop in which we are going to be doing the dumping of tokens and purchasing tokens from the victim. So I have the expansion of the loop right here. So with every iteration, for good measure, I will be doing it 20 times. In every iteration, we approve the ERC20 tokens to be sold on Uniswap, and we sell them on Uniswap for ETH. And then we take 10% of the tokens that the victim pool holds. So here we take the balance of the pool, we cut it by 10, and then we take a look how much ETH we actually need to purchase these tokens with, and we call the victim and say, hey, let's buy all the tokens. And this happens in that loop 20 times. When we are done, we are gonna end up with all those tokens and all that ETH, right? So I said at the end, we go back to Uniswap and we buy back all the tokens that Uniswap is able to sell us with this ETH. So we call here to Uniswap and swap those tokens back for Ether. And then we close the transaction by transferring tokens back to the flash loan provider so that the transaction doesn't revert. So that's our exploiter. So how does that work? On a hard hat, I spun up a local simulation of the network, and I deployed the system and launched the attack. And from those logs that I instrumented the smart contract with, we can actually see the progress. So we start with 30 million tokens paired with 30 WETH in Uniswap as the liquidity. This is our starting balance. So victim has 30 million of these tokens. Flash loan contract has 30 million tokens that can be borrowed. And then we start that loop in which we always purchase 10% tokens from the victim's balance. So in the first iteration, we are purchasing 3 million tokens for 0.79. That's what Uniswap says and dictates that the price should be. In the next iteration, 2.7. And then you are actually going to be, you're actually seeing that that balance in the victim is being depleted because in every single iteration we are purchasing less and less tokens. So eventually we finish right here. That's my 20 iterations of the hack. And this is the resulting state. So the exploiter, after everything in here is completed, ends up with 20 million tokens. The victim pool has some measly 3.6 million left, but has received almost no ETH for it, right? You can actually see that we are selling for extremely, extremely cheap. And because the flash loan provider required the token loan to be repaid, it ends up with exactly the same balance that it had before. If you want to see this running, if you want to see this set up, feel free to find me in the booth. I actually have my laptop with me so I can show you how that works. So this is what would happen on Hardhat or any kind of Ethereum network that currently exists except for Zircuit. Now let's take a look how it looks on Zircuit. Can I please ask for the video to be played? So this is my terminal. I have prepared 2 addresses and loaded them with some ETH. We will see those addresses before. And what's happening now is that I'm deploying the entire system on Zircuit testnet. So we have a deployer. Here it starts with 0xD. It's a different address that I will be attacking from. And the script is deploying some mock token. That's the token that we will be stealing, WETH9, Uniswap factory, so that I can create a liquidity pool. It's going to be deploying the Uniswap router that I can work with. It is going to deploy the flash loan provider. It's going to deploy the Uniswap V2 pairs, to which we will be actually loading this liquidity. And then it's going to pair that 30 million tokens with 30 WETH inside of Uniswap. It's going to deploy the victim pool and it's going to load the victim pool. Can I please ask for the cursor to me move so that the entire command is visible? Right here? Perfect. Okay. So then in the second step, can we please pause the video for a second here? So I have deployed the attacking infrastructure. What you were able to see right after are some commands. So actually in Zircuit, we have created 2 RPC calls in Geth where you can retrieve the content of the quarantine to double check what was quarantined and whether a single transaction was quarantined. So this was a call that allows me to list all the transactions that are currently present in the quarantine. When we now restart the video, you will see another RPC method that can be used to check a single transaction. Please, let's play again. So it's right here. This is reference to our sequencer, and there was an RPC call in there. Now we are calling quarantine, and you can see that there is nothing in there. So now I'm actually launching the exploit. This is the exploit transaction. And when it launches, we will see that nothing is really going to be happening because we are waiting for this transaction to mine. But because Zircuit currently analyzed it and realized that this is a hack, it quarantined it. So it will be stuck up until the moment when I kill it. So we will see that. We've just killed it. And if we list the quarantine, it's no longer empty. That would be an experience for the hacker. Then if we want to check a transaction, I'm going to check the transaction in here. I'm going to fill in the transaction hash. And it was actually wrong at transaction. So right now, quarantine is going to tell us, no, this was actually not quarantine. But if I take a copy of this hash and paste it into that check right there and run the call, we will see that we didn't see anything. There was a response from the quarantine that actually told us that this transaction was quarantined. So again, if you want to see it in a slower pace and live, I can show you in the back. Please come find me to the Zircuit booth. So this is how Zircuit testnet actually prevents hacks. We are publishing a transaction overview on our block explorer so that you can see the content of everything that was ever quarantined on Zircuit. This is how it is going to look, and that's about it. So I am pretty much out of time, so I will not be telling you today about how this is implemented. It is implemented based on Geth, so I'm going to skip a few slides. What I want to show you is that we actually have some more talks about this concept. So if you Google Zircuit and ETH Denver, you will find information about what happens with transaction in the quarantine, how performant the oracles are, and so on. We also have an academic paper about this concept. So if you go on archive, it's open, and search for Zircuit, sequencer level security, or my name, that paper is going to pop up and is going to give you much more answers to questions about, can we DDoS this, how strong it is, what are some backtesting data, and so on. The spoilers are, yes, this is DDoS resistant. It is capable of catching pretty much all the possible attacks that are currently happening on EVM chains. And that's where we are going to end the talk.